So if we understand that we can break bonds by putting in energy and we release energy when new bonds are formed, and we've got a decent understanding of energy level diagrams, we can calculate an energy change for a reaction. Let's take an example. This is combustion of methane again. I wasn't feeling particularly inventive. And so we've got an exothermic reaction here, and I might be asked to calculate how much energy we're going to get out of this reaction. And we can do this by working out, if I was to break up this methane and oxygen into all its individual atoms, and I could work out how much energy that took, and then if I could work out how much energy was released from putting them all back together again, I could work out the energy change. The energy change would be the difference between them. So what I've got to do is I've got to think about, okay, well, what bonds are we talking about here? Now, methane, I've just displayed the formula of methane and oxygen there. Quite often this is given in the exam question. But we have methane drawn out there and oxygen drawn out there. You can see that we've got 4 carbon to hydrogen single covalent bonds that we're going to break. And with the oxygen, there are 2 oxygen molecules and each one has a double bond. And so we're going to break 2 oxygen-oxygen double bonds. On the other side, we've got 4 oxygen to hydrogen single covalent bonds there, because we've got 2 water molecules and they've got 2 each, so that's 4. And then with the carbon dioxide, we've got 2 double carbon to oxygen bonds. Now, you will find in an exam question a table of data, and that table of data will tell you how much each bond is worth. Here's the table then. So for CH bonds, we can see that we have 413 kilojoules per mole per CH bond, and we have 4 of them, so we're going to multiply 413 by 4. And it's the same with everything else that we've got there. We've got 2 OO double bonds, which is 2 times 4, 9, 7. And we've got 4 OH bonds on the right-hand side in the all bonds made arrow. I've got 4 times OH, so that's 4 times 4, 6, 3, and then we've got finally 2 CO bonds, double bonds, so we've got 2 times 803. So we've taken each type of bond, we've worked out the energy for that, and we've multiplied it by how many of that type of bond there are, and then when we've done that for each bond, we're going to add all of the ones in the bonds broken column up, 2, 6, 4, 6, and we're going to do the same for the bonds made. You can see that I've got my total there, 3, 4, 5, 8 on the bottom there. I've just added those 2 values up together. And you can see, therefore, that on the right-hand side with the bonds made, the value there is larger than the value with all the bonds broken. And that's to be expected because it's an exothermic reaction. We know that that should be true, and this is a good way of checking it. I would incidentally always draw out a diagram, an energy level diagram, while I'm doing this, just because it helps you avoid some of the simple mistakes, like for example forgetting to multiply something or missing out a bond from the molecule. If you end up with an energy change which is endothermic when it should be exothermic, you know you've done something wrong somewhere. Yeah, we're going to then take those 2. We're going to take the bonds broken, and we're going to subtract the bonds made, and that's going to give us an energy change. Okay, so the bonds broken minus the bonds made is going to give us minus 812 kilojoules per mole. Can you see that the energy change of the reaction, the arrow is pointing down? The minus means we're going down in chemical energy. Now, at GCSE, if you miss off the minus, it doesn't actually matter. All the examiner really wants to know is that you understand that it's the difference between them. But the proper way of doing it is to show it's exothermic by putting a minus sign on the front of it, because the chemical energy is going down. Endothermic example. So I'm going to take water, I'm going to break that up into its elements. This is an endothermic process. You can see that, again, I've drawn the energy level diagram out. All bonds broken, all bonds made. If we're talking about all bonds broken, we can see that we've got 2 H2O. 2 H2O looks like that. And so that's going to be 4 OH bonds. The bonds made, we're going to make 2 hydrogen molecules, so that's 2 HH bonds, and we're going to make 1 OO. And so you can see I've put the numbers up on the side there. We'll just do the calculation. So we're going to get 4 OH bonds on the bonds broken side, and we're going to get 2 hydrogen-hydrogen bonds and 1 oxygen-oxygen bond, double bond, on the all bonds made side. So we take the numbers from that, we plug them in to the equation. 4 times 463 gives us 1852, and that's the total for that side. And then we have the 2 436s, which gives us 872, and then we have 1 lot of 497, which gives us a total of 1369. So now if we work out the change of energy for the reaction, bonds broken minus bonds made, so the bonds broken, again you can see on this side that the bonds broken is larger than the bonds made, and that's expected because we know that this is an endothermic reaction. So we're going to take 1852 is larger than 1369, so we take the bonds broken, 1852 minus 1369, we get a positive value this time of 483 kilojoules per mole. And again, as the chemical energy has gone up, it's an endothermic reaction, so that's why it's positive. But again, it doesn't matter at GCSE as long as you've got the correct difference. So what if you don't know whether a reaction is endothermic or exothermic? What if you're trying to find out whether this is going to be an exothermic or endothermic reaction? C2H4 is ethene, and we're going to react that with chlorine. That will make the molecule, if you look up at the top, you can see on the right hand side, that's a molecule called 1,2-dichloroethane, and that's not important really. You just need to know that that's what it forms. So I've put the schema up at the top. The first thing to do here is work out what are we going to break. Well, we're going to break into atoms. We're going to break 4 CH bonds there. You can see we're going to break a Cl-Cl bond, and can you see that the double carbon-carbon bond in the middle is changing into a single bond? So we're going to break that as well. So we're going to break up the carbon-carbon double bond, 612. For that, we're going to break up 4 H to C bonds. That's 4 and 3 times 4, 1724. And then we're going to take the Cl-Cl bond, break that up as well. That's 242. And we get a total of 2518. So, is it exothermic or endothermic? Well, to find out, we're going to calculate the bonds made. We know that the bonds broken will be an upwards change. Again, I would draw this out as I was doing it. So the upwards arrow with that number 2518. We're going to say, right, okay, if all the bonds are made, we've got 4 CH bonds again, which we know is 1724 already. We've now got a CC bond being formed, which is 348, that's in the table, and we've got the 2 C to Cl bonds which are formed, so that's going to be 2 times 338. And if we put that in a table or something like that, we can work out that the total there is 2748, and because that is a larger number in the bonds made than the bonds broken, we know that this must be a larger arrow going downwards, and therefore it's going to be an exothermic reaction. Now, if you're answering this in an exam, the important thing to say is that the energy released when all bonds are made is greater than the energy required to break all of the bonds. Okay, that's the key information there. Sometimes they actually want the value there. Okay, so you might want it's good to put the actual number in as well. But we can do more with this. We can work out exactly how exothermic it is by taking the energy change, 2518 minus 2748, gives us minus 230 kilojoules per mole. Okay, and so we've worked out that this is going to be an exothermic reaction, and it's going to be fairly energetic. So to summarize, take the bond type, substitute the number for that bond type, and multiply it by the number of bonds. Add up the total for all of the different types of bonds that you've broken. Add up the total separately for the number of bonds that you made, and then take bonds broken minus bonds made, and that will give you energy change.